Hello everyone, this is Yujie Chen from National University of Singapore. Today I would like to share my research topic that is the universal method on charge carrier mobility and series resistance extraction in two-dimensional field effect transistors. So 2D semiconductors for FET applications has been enormously studied in the last few years. However, we found that the contact resistance for 2D FETs is typically very high. And indeed, if we look at the benchmarking figures of the contact resistance, we take moly disulfide as a case, we can see that the available contact resistance values are actually higher than the silicon MOSFET ones. And this means that continuous effort is required to further bring down the contact resistance value in order to make these 2D semiconductors at least competitive with the state-of-the-art silicon technology. On the other hand, establishing an accurate yet simple extraction technique to characterize the contact resistance is also another critical aspect. So this will be the focus of my research topic. So in my research topic, I would like to establish a universal parameter extraction model for 2D FETs. And I will start with the extraction model derivation and followed by the experimental validation. And also I would extend my extraction procedure to various types of 2D semiconductors to confirm the universality of our proposed extraction model. And at the end, I would like to summarize my presentation. So before we jump into the extraction procedure, one of the most critical aspects is to establish a universal mobility expression. So we take this power law mobility expression, and we believe that this could be a universal expression for mobility. And this is because that there's a control factor over here, which is the power term gamma at this part. So if gamma is equal to 1, then basically mobility is a linear function with respect to Vg minus Vt. If gamma is a negative value in between 0 and -1, then basically the charge conduction is dominated by surface and phonon scattering events. And if it's greater than 0, then the carrier conduction is likely to be dominated by the trap or defect states at the interface or in the channel itself. So we believe that this could be a universal expression to model our mobility expression with respect to the gate voltage. So we take this mobility expression and then we plug into the ID equation with the consideration of the contact resistance. We will be able to get this analytical drain current expression under linear regime. So K is the geometric factor defined by the constants over here, and the contact resistance is over here. So the first step we take is to define a Y function. So Y function is defined by the drain current divided by the square root of drain voltage times transconductance. So if we take the drain current equation over here and plug into our definition of the Y function, we will be able to get this analytical term of the Y function over here. So it is important to note that if gamma is not equal to 0, then basically Y function is not a linear function. For parameter extraction, we always prefer a linear function because we can do a simple linear regression to extract the parameters that we are looking for. So in order to make the Y function into a linear function, we define a new H function concept. So the H function is defined by the Y function, the integral of Y's function itself over the range of Vg and divided by the Y function itself. So by taking into the consideration of the Y function over here and plug into the definition of H function with this definition, we will be able to get a nice and clean linear function at the shown over here. So if we can calculate H function and when we plot against gate voltage, then the slope we get is actually the bunch of term over here. So from slope, we will be able to determine the gamma factor, which is the power term in our mobility expression. And since the gamma factor has been extracted, we can actually make the Y function a linear function. How do we do so? We can define a new function that is called gamma Y. So gamma Y is divided by the root of 1 plus gamma over 2 of the y function, and then the above equation becomes this equation over here. So by calculating gamma y function, plotted against gate voltage, the slope we get is this term over here. And since gamma factor has been known, so K, the geometric factor, can be determined. And from the x-intercept, we will be able to calculate the threshold voltage. So far, by doing all these linear regression, linear extrapolation, we can determine gamma factor, threshold voltage, and the K value over here. So if we look back to the drain current equation, the only unknown parameter left is actually the contact resistance. In other words, contact resistance can therefore be extracted. So this is pretty much our extraction procedure. So the next step is to apply our extraction model to a real case study. So to validate our extraction model, we apply this procedure on a nanoribbon black phosphorus device with a top view shown over here. So first of all, we measure the drain current, the transfer characteristics at drain voltage of 0.1 volt from cryogenic temperature of 3K all the way up to 300K. Then we do the extraction by our proposed technique. First of all, we can get the contact resistance with respect to the gate voltage. One thing interesting to know is that the contact resistance actually decreases with increasing temperature. This suggests that the carrier injection at the contact part is dominated by the thermal-activated process. On the other hand, we will be able to construct the intrinsic carrier mobility given that the contact resistance has been extracted. So the extracted mobility is shown over here with respect to different gate voltage under different temperatures. So again, it can be seen that the mobility follows a thermal-activated process. So far, we are able to extract the intrinsic properties of our channel region and also the contact resistance at the metal semiconductor interface. The next step we would like to validate is whether this is universally applicable for different types of 2D semiconductors. So we apply this procedure to various types of FETs. This involves black phosphorus, indium selenide, MOS2, MOS2, RES2 tungsten disulfide with top gate and bottom gate configuration. So the open dots are those from the measurements, and the solid lines are those constructed by our extracted parameters. One can be clearly seen is that the fitting results excellently fit with those from the experimental results. And this suggests that our proposed technique could be universally applicable for different types of 2D semiconductor for FETs application. So this brings us to the summary of today's presentation. First of all, we proposed a universal extraction technique that could extract the contact resistance value as well as the charge carrier mobility of our 2D semiconductors. And this can be validated by comparing the fitting results with those from the measurement results. And on the other hand, we extend our study to TK simulation, and also we validate our extraction model with different types of 2D semiconductors. This is pretty much my presentation. Thank you for your attention.